My name is LeAnna Weakley, and I am based in the Detroit area. And I'm going to be talking about our MPXV automotive grade power inductor series. So what we'll cover today are automotive applications that these inductors go into, requirements and technology trends that are leading to the use of these types of inductors. We'll go over advantages and limitations of this inductor technology. Then we'll do a performance comparison, and finally product lineup and roadmap. So let's get started. Automotive applications, there are a whole lot that these types of inductors will go into. Definitely not limited to this list, but it is a good reference for you to see just how many applications that MPXV series can go into. I'm not going to read through this, but you can see that goes into everything from LED headlights and ECUs all the way to electronic power steering and ADAS systems. So there are a wide range of automotive applications that these types of inductors are being used in. So within those applications, there are some areas, specific areas where these inductors are being used. The first of which is a pi filter application, and it's called a pi filter because it looks like the pi symbol, as you can see over here on the right, and it's two capacitors and an inductor. These are used for EMI filtering and are most common in the inputs of ECUs and applications like that. And they're connected to the battery voltage rail. So whether that's 12, 24, or 48 volts. The second application area is a DC to DC converter output filter application. So unlike the pi filter, this isn't filtering EMI noise, it's smoothing your current. And whether it's a buck or a boost DC-DC switching converter or LLC soft switching converter, we're seeing more metal composite type inductors such as the MPXV series being used because frequencies are going up. So I'm also going to talk about application requirements and technology trends and what is leading to the use of this type of technology. The first of which is a decrease in package size, the need for enhanced EMI behavior, and reliability of components. So we'll go into each of these a little bit more in detail. So a decrease in package size. As you increase the frequency in your application, the amount of capacitance and inductance that you need will also decrease, which means you can use smaller components. Now, those smaller components, however, will have to carry the same amount of current as the larger components that they're replacing. So the power density for these smaller components will increase. So efficiency will become much more important to you unless you want to change how you're managing your heat, your thermal management. And this is also why soft switching is becoming more attractive, and wide bandgap technologies such as silicon carbide and gallium nitride and high-speed silicon, because they do have lower losses, and you can get up to a 50% reduction in your losses with this type of technology. We're also seeing the need for enhanced EMI behavior. So as you increase your switching speed, this definitely influences your high frequency harmonics and your filtering demand. So let's look at an example. Here we have an application that's first being switched at 10 microseconds, and down here it's being switched at 40 nanoseconds. If we look at 100 kilohertz here, you can see that the noise at 10 microseconds is 80 decibels, whereas when it's being switched at 40 nanoseconds, it's 90 decibels. You'll also get higher spectral power at higher frequency ranges. So you would, at higher switching frequencies, you would need parts with enhanced EMI behavior in order to handle these higher noise values that you would see. Now, especially in the automotive market, reliable components are being required. There's always been the AEC Q200 within the automotive realm that requires parts to be reliable, but especially these days, as more and more electronic components are being put in vehicles, the need for reliability is increasing. So you can see here that in 2030, it is projected that about 50% of your total car cost will be in electronic components. That means that zero defects and low fit rates and higher ambient temperatures will be necessary. Now, when you talk about reliability, you also want to think about shielding, insulation resistance, the capability of the part through the wash process, and your mechanical aspects of the component. You don't want it to break or crack. So about 3 years ago, KEMET purchased Token, which is a Japanese company. And this is where we've got our inductors and our magnetic products from. And they have more than 40 years of experience in the automotive with these inductor products. So our components are AEC Q200 compliant, and our plants are qualified to IATF 16949. And you can see our certificates of registration over here on the left for both our Vietnam and Chinese plants, which is where these inductors are produced. So we talked about reliability. That brings us to losses. Losses are seen as heat, so you want to keep them as low as possible. There are 3 types of losses for inductors that you want to take into account. The first is the DC copper loss, or the DCR. This is the resistance of the windings of your inductor. The next is AC copper loss, and this occurs with AC currents or switch DC currents. And this is the result of the skin effect. So as you raise the frequency, your electrons move to the outside or the skin of your conductors. And that reduces the cross section of your wire, which increases your resistance. So you get losses that way. And then the last is your core loss. And this is the loss of your actual magnetic material. And that's due to alternating flux conditions. So again, in an AC or a switch DC application, you would see core loss. And that would include the hysteresis effect and your eddy currents. So as you're changing your electric field from positive to negative, like you would in an AC application, your magnetic field would also shift with that electric field. And that is what would cause this hysteresis effect, your eddy currents, and you would get that friction in your heat. So speaking of heat and losses, we'll talk about thermal heat rise. And that depends on your losses produced by your thermal resistance. So you can try to keep these low by maybe making the layers of your PCB, that copper layer, thicker, make it work more as a heat sink. The air gap of your coil versus your core also plays a large role with the inductors. So the more space you have between your coil and your core, the worse your heat rise will be. Airflow also will help, but this usually isn't possible within an automotive ECU. So let's look over at the right at an example of the heat rise of one of our MPXV series inductors on an FR4 board. So with this part, we've put 9 volts in, an output voltage of 2.5 volts. We have 3 amps on the part, and we're switching at 500 kilohertz. And with all of this on the part, we're getting an increase in temperature on the part versus ambient of 9.2 degrees C. And this total power loss, this heat rise, is based on your DC current, which increases as you increase your current, and the relation of the voltage change with your part. So the 12 volt input versus a 3.3 volt output would give you an 8.7 volt voltage change. And the larger this voltage change, the higher your losses will be. And then also higher frequencies cause higher losses. So we'll look back at our example, and if this 9.2 degrees C, we think, well, we want to make that lower. We could do a lower switching frequency if possible. We could try to lower the current that the part is seeing, or we could see if we could change the input and output, the difference there. So I talked about the gap in an inductor structure having an impact on the thermal capability of the part in the last slide. There are 2 types of inductors that we'll talk about today. One is a metal composite inductor here, and the other is a ferrite inductor. And the structure of these is a little bit different. The ferrite inductor is an assembled type, which means you have 2 pieces of your core, and they're assembled together around your conductor. And that leaves an air gap between your core and your conductor wire. Now, a metal composite inductor has a molded core. So that means that you don't get that air gap that you do in a ferrite inductor. And because you have less of a gap between that conductor material and your core, you have higher, a more stable inductance with your temperature. You can also have a smaller package size with the molded core because you don't have that extra space of the air gap in between the conductor and the core. Now, the lack of the air gap also helps with your EMI performance of the part. So here we have a molded metal composite inductor similar to our MPXV series. And this is a ferrite assembled type inductor. And if you look over here, you'll see that the magnetic flux leaking from this assembled type inductor is much higher than that is leaking from the molded type inductor. So not having that air gap is helping with the shielding of your part. And we can talk a little bit more about the differences between ferrite and metal composite inductors. The first of which is saturation, and we'll look up here. The green line is a ferrite assembled type inductor. And you can see there's a point here where the current, where the part saturates. So there's a current value where your inductance starts dropping off. The yellow line is your metal composite inductor. And you can see that it is a very stable, soft saturation curve. The trade-off is the inductance value. So you can see that the amount of inductance you can get with the metal composite is much lower than what you can get with the ferrite material inductor. Core loss is also something that varies depending on whether or not it's a ferrite type or a metal composite inductor. The assembled ferrite type will have a lower core loss than that of the metal core. So there are advantages and disadvantages of each type. And that brings us to our METCOM power inductors that we're talking about today. We kind of took the beginning of metal composite and stuffed it together and called them METCOM power inductors. Specifically our MPXV series. This is our automotive grade series. And this is our part numbering system. This is our product version 1. So these were just launched. And then you've got your size code. The L is for power inductor. And then of course your inductance range. We have a wide variety of our MPXV series. Again, they are AEC Q200 qualified, produced in an IATF 16949 production plant. And they do go up to 155 degrees C. And we have over 200 parts within this automotive grade series. So some of you might remember that last year we released our MPX series in 2019. And the MPXV is actually the automotive version of that MPX series. So V stands for vehicle, so automotive grade of the MPX. Both of these series will cross to Vishay's IHLP series. And that's great because, as you probably know, inductors don't usually cross to one another very well. There is no common size or pad layout within the industry for inductors. So by providing this series that crosses to the IHLP, customers have the option of a second source. Earlier, I talked about the applications where these types of inductors would be used. And the first was a pi filter application. So the main parameters that you need to consider when using these parts in a pi filter application is first off the RDC. The lower the RDC, the higher the efficiency. And the second is the resonance frequency. The resonance frequency will drop with higher inductance values and increase with smaller case sizes. So we have an example over here on the right. This is, all of these parts are 6x6 millimeter size. All of them are METCOM MPXV inductors. And you can see where the curve starts going up. That is the resonance frequency of the part. And the resonance frequency of the higher value inductance, higher inductance value inductors, excuse me, is lower than that of the lower value inductors. And if we put a smaller case size, say a 5x5 millimeter instead of 6x6 and the same inductance values on this chart, we would have higher resonance frequencies for those, because resonance frequency will increase with those smaller sizes. Now in this type of application for an EMI filter, EMI pi filter, AC losses can be pretty much ignored. So the ripple current in this application will be fairly low simply because we're filtering out EMI noise. We're not smoothing any kind of ripple current. So the losses are strictly related to the DC resistance of the inductor coil. The second application I talked about earlier was DC to DC output filtering applications. For these types of applications, the main parameters to consider would be the Q factor. The Q factor is a great measure of efficiency. It relates inductance to the resistance using this equation. You can see over on the right, the blue curve. The sweet spot for our METCOM MPXV inductors is somewhere between around 700 kilohertz and 3 megahertz. This is where the Q factor is high and the losses are low. Now, saturation behavior, we talked about saturation a little bit when we discussed ferrite and metal composite inductors, how it has a very smooth saturation. So that is something to keep in mind, as well as what that saturation behavior is. Bigger current transients are still going to be filtered, but with a lower inductance. So if you had a ferrite here, you would have you know, a higher inductance value, but you would have a steeper saturation. And we did put a curve up here, this yellow curve, for a ferrite to kind of show where the Q value was for that as well. So they would kind of be better for lower frequency applications than these METCOM inductors, which are in the blue. So we said these parts will cross to the IHLP by Vishay. So let's look at how they compare. These are two 10 microhenry inductors. You can see that the sizes of the exact sizes of the parts are a little bit off, but the pad layout that is suggested is exactly the same. So even though our part is 0.5 millimeter longer than the Vishay IHLP, it can be a drop-in replacement because it fits directly on the pads, the exact same pad layout as the IHLP. Our DC resistance is a little bit lower in this comparison, and we do have a higher rated current. Now, I know you're looking at the saturation current and thinking, how can you say these are comparable when your saturation current is lower? So let's take a look at that. This is an example of our MPX series data sheet. You can see that we provide 3 different current values. One is the RMS current, and that's the current at which we have a 40 K temperature rise. Then we give 2 saturation currents. One is a 20% inductance loss, and one is a 30% inductance loss, and you can see that here. Now these values, the temperature and the inductance drop values, are not common among all suppliers in the industry. So you need to keep an eye on these and make sure that you are comparing correctly. So this is an example of a competitor part. As you can see, they have 3 different types of current as well. Their temperature change is 40 degrees, the same as ours. And they have both 20 and 30% inductance drops as well. So we're good for now. But the big difference is the operating temperature range. And their part is from -55 to 125. Our part goes from -55 to 155. So keep that in mind. So looking at their RMS current, we see that they can have a maximum of 3.3 amps at 85 degrees C before they reach that 125 degrees C operating temperature. So they can't get up to that 125. This is an example of another competitor. And at first glance, it looks like this part is really great. Their saturation current at 20%, which ours is as well here, is 4.5 amps, and ours is 4. So you might say, oh, let's use this part. But you do need to look a little bit further at their RMS current. And the temperature at which their part rises 40 degrees is 2.2 amps, whereas ours is 4.5. and their operating temperature is -40 degrees up to 125 degrees C. So what this means is that they can have a maximum of 2.2 amps with a 40 degrees C temperature rise at 85 degrees C before they hit that 125 degrees C. So they can't actually use this 4.5 amps that you see in the saturation current without overheating the part. Now let's look at our part. We have a maximum of 4.5 amps at 115 degrees C. You can see that our RMS current and our saturation current are pretty close together, which means you can get up to this saturation current, not saturation, RMS current, excuse me, without overheating the part. So you can have 4.5 amps on this part at 115 degrees C, or you can have over 4.5 amps at 85 degrees C, depending on your ambient. So let's say you like the MPXV series product, but you're looking through our data sheet and you don't see anything that exactly meets your needs. Don't give up. We do offer customized designs for this type of product. Now, be aware that we are not magicians. We can't defy the laws of physics and give you a part that that just can't be made. There's always a compromise between the RDC and the saturation. So the more volume your coil represents in the mechanical space of your part, the lower your RDC, which is great. But then less space is remaining for your core material, which means you have a lower saturation capability. So there's always a compromise between those two. Parameters that are important to an electronic designer, they can vary depending on your application. Type of heat sink you use, you might be able to pull more heat out of the part and use, allow for a little bit more self-heating, things like that. Our standard designs will focus on what makes sense on a standard FR4 board. So as you saw in my last slide on our data sheet, our saturation current at 20% is kind of in the range of our rated current. That's how we rate our parts. But we can alter that based on our, our customers' needs. Now we do have a lot of design tools available for you at our engineering center. There's a link here, the engineeringcenter.com. And that's where you can find a lot of our tools. If you're not familiar, we do have a tool called KSIM, stands for KEMET simulation. And this was traditionally mainly for our capacitor products. Again, if you're not familiar, there you can find DC bias curves, frequency curves, temperature curves, things like that for our capacitors. We are launching a version 3.0 on April 27th. That will include our inductors, and this inductor series will be included. And the simulations that will be on that KSIM tool will be inductance versus current. You can see the temperature rise with your current, and there will also be power loss curves. And I've included a couple examples of kind of what those curves will look like within the tool. And that will be at this site here at ksim.kemet.com. So keep an eye out for that in the coming weeks. So what's next? As discussed, we released our MPX last year in June and October. And the MPXV series was just released. And we have 213 parts. And we are working on our MPEV series that will have an operating temperature of 180 degrees C. And we also have automotive grade MPHV series that is also under development, And those are very large inductors that go up to 80 amps. Now our MPXV series that we discussed today is available from distributors. So you should be able to find those available throughout whatever distributors you use. So in conclusion, our METCOM technology is key for our automotive applications. We offer over 200 part numbers and they are all AEC Q200 grade. Our MPXV series is matching and exceeding the industry performance. And our MSA, which stands for Magnetic Sensors and Actuators Business Group, is ready to receive orders for these types of parts now. Thank you very much. If you have any additional questions, we do ask that you use this link, contact us. I will be answering questions now, but if you have questions or think of anything afterwards, we do ask that you use this link here to submit those to us.